I think this is recording. Can you like write something on the board so I can see if I need to move closer? Write something nice. Yeah, I think it's fine. Hold on. We're gonna zoom. Wait. We're zooming. There we go.
Is it okay with the light on?
I think this is fine.
Excellent. Are we ready? Did you see your paper and your worksheet are up? I mean, they've been up for a while, but oh my God. So today, other than a nice fat kitty to look at and make fun of, we're going to learn about how insulin resistance occurs. So how is everything we've learned about kind of result in insulin resistance? What are the repercussions, et cetera, Use Ricketts font. So first thing I want to do is remind ourselves about the things.
What's your number?
Can you not go this far up, Bernadette? How far up into the board does it go?
No, you're good.
Okay. So first thing, let's just remind ourselves about the things affected by insulin, which we did on the first day. And then that will make more sense when we think about what happens during insulin resistance. So things affected by insulin and or glucagon. Okay. So one of these, this is just a complicated looking slide that's meant to show you the insulin pathway. Don't worry about this part, okay? And don't worry about these guys. All right, but it's just meant to show you, like, here's the insulin pathway. Ultimately, AKT gets activated and a bunch of crap happens. I kind of like this part, so that's why I put it in here. So one thing that happens is what? Or one thing affected by insulin is what? Did we say that first day? That's also kind of shown. You can see that this represents what type of cell. And this is. And this is. So what's one thing that is affected by insulin and or glucagon? What pathways?
Glycogen synthesis.
Yeah, so remember glycogen synthesis and breakdown. And again, we'll come back to this in a bit. I just want to put it out there. Which we went over during that first day. What's another one?
Glycolysis.
Glycolysis, and the flip of that is
Gluconeogenesis.
good. And we learned more about this, right? We learned how this is controlled via that like weird bipolar walking contradiction of a protein that's half kinase, half phosphatase. So we learned more about that the first day. Okay. What did we learn about last week? That is also
Glut4.
Hmm?
Never mind, that's not what you learned last week.
What did we learn last week about what type of metabolism?
Fatty acids.
Yeah. So fatty acid metabolism or lipid metabolism. So the breakdown and synthesis of that guy. Okay, so again, under insulin conditions, we've got a lot of food around, so we're going to store it as glycogen, we're going to store it as lipids. So it's going to increase glycogen synthesis, increase fatty acid anabolism or lipogenesis, whatever you want to call it. And then also in the fat cells as well, increase lipogenesis, decrease lipolysis, right? And then the last thing that's mentioned here that we haven't really covered in any sort of detail yet, but mentioned briefly that first day is this also happens to be the main function of insulin.
Glucose transport.
Yeah, glucose transport. So the GLUT transporters. Okay, this is affected by insulin. And specifically, what you guys can see here is a particular one called GLUT4. So I just want to briefly go over your GLUT transporters, and then we'll get into the other stuff. So you have a bunch of GLUT transporters, so you have 4 main ones that I just want to go over briefly. Did anybody ever cover the different GLUT transporters in any other classes? Excellent. Okay, so we've got, you can imagine, since there's a GLUT4, there's probably a GLUT and a GLUT1, as I was going to start that one, but yeah. So GLUT1, this is kind of like for your basal glucose uptake. Basal meaning, you know, just kind of your steady background. Let's always make sure we're taking in some glucose. Okay? So if this is the one that just sort of always makes sure that you're able to get at least a little bit of glucose in, which tissues do you think express this one?
Your muscle?
Everything. Yeah. So this is like all tissues express GLUT1. Because again, it's kind of like your background glucose transporter. Okay? This guy has a high affinity for glucose. Does that mean he has a high Km or a low Km? Good, low. If you have a high affinity, it doesn't take much to get you at half saturation, which means you have a low Km. Good, so the Km for GLUT1 is roughly 1 millimolar. Okay. So it has a high affinity, but remember, this is just background glucose uptake. So what's one way, if you've got receptors that are really bind glucose really well, what's one way of making sure that you don't take up too much glucose? So it binds glucose really easily and will take it up, but we don't want to take up too much via GLUT1.
Negative feedback?
Negative feedback would be one way. What's something like simpler? So you have a cell membrane.
Congregational change.
I love that you guys put all these things that drilled in your head. I was actually going simpler than that. So this guy can take up glucose really easily and quickly. The way that we can counter that to make sure we're not taking up too much is just to have very low expression on the cell membrane. Okay? So in other words, there's just not going to be, it's going to be very small amounts of it on the cell surface. We're going to have low expression. Yeah, and I like that you guys both brought up elements of regulation, and that's what I like that you did, because GLUT1 isn't really regulated. So we need other glutes that are regulated, because we want to increase our glucose transport into the cell when we've just eaten a meal and stuff like that. Okay, and there's other times we'll want to do that too, which brings us to GLUT2. Sorry, Katie, we'll get to GLUT3 in a minute. Usually it goes like in numerical. So GLUT2 is going to be in pancreatic beta cells. That is where it is primarily expressed. You'll also find it in the liver and kidney a bit as well. Okay. And what this guy does is he's going to trigger insulin secretion. So what do you guys think about the Km for this guy? If you only want him to work under conditions of high glucose. High Km. This Km is going to be more like around like 15 to 20 millimolar. The way this works is kind of cool, by the way. What's going to happen if you bring in a bunch more glucose into the cell? If I'm just a regular old cell, I have more glucose, it's going to go through glycolysis, citric acid cycle, electron transport, you end up making more what? The point of like glucose oxidation is to make ATP. Yeah. So the way this works is the increase of ATP is going to close potassium channels. And that sort of different ionic environment is going to open calcium channels. Which of course will increase the concentration of calcium. Okay. This increase of calcium in the cell is what triggers, some of you might already know this, but insulin is already ready to go. It's in vesicles in your cell, well, in the beta cells. So insulin is already synthesized, ready to go, packaged up in these little vesicles. It just needs the signal to like have the vesicles fuse with the cell membrane and spit out the insulin, okay? And it's this calcium that does that. So the calcium is going to cause the vesicles that have the insulin in them to fuse with the cell membrane, and then that will sort of spit out the insulin into bloodstream. So it's just kind of neat the way it works. You could do like a whole class on it, but we won't. All right, then we got some gluten-free. Katie's favorite.
No.
You know why? It's in the brain. So, you know, your brain would like to get a little extra glucose, please. So your brain and neurons are kind of the main gluten-3 recipients. The placenta and testes also express gluten-3. Okay, and the Km for this guy is also about 1 millimolar. So those tissues just get a little bit extra all the time.
Sorry, can you say again what the vesicle squeezing does?
Oh, up here?
Yeah.
So if you can imagine, like, I'm a cell, and I have these little vesicles that have insulin in them, and that calcium is going to trigger this vesicle to then, like, the membrane of the vesicle will fuse with the cell membrane, and that kind of opens it up, and then out the insulin goes. Just sort of like pushes out the vesicle. That's all I care about with gluten-free. So far, guys, none of these GLUT transporters have been regulated by anything. Granted, GLUT2 regulates other things, but it itself, the expression of GLUT2, we didn't mention anything about its regulation. So the last one, and the one that we're going to care most about, the magical GLUT4. Okay? GLUT4 is in muscle and fat cells, as you can see from the slide. Okay? So glucose transport, GLUT4, GLUT4. Okay, and its Km is about 5 millimolar. So it's like the Goldilocks, if you will, of the gluten transport. And again, we're going to care about this guy because his expression is regulated by insulin. So expression on membrane is regulated by insulin. So he is a downstream target of AKT. So AKT, when it's activated, so GLUT4 is also in storage vesicles. And then AKT is also going to cause AKT is also going to cause them to fuse with the membrane. And so GLUT4, instead of being secreted though, GLUT4 is in the membrane. So you can think about what we said before. If I'm a cell and I have a vesicle and GLUT4 is in the membrane of that vesicle, when it fuses with the actual membrane, now it's become embedded into the cellular membrane. Okay. So these things like insulin and GLUT4, they have to respond quickly to different nutritional situations. So that's why they're ready to go. They're just hanging out in the cell. They need a signal to then fuse. Yeah?
What does it say next to GLUT4?
Says from storage vesicles.
Oh, okay.
You know. So much more clear now. Anyway. Okay, so we know why the muscle would want, so again, this is going to be responsive like, oh, we just had a meal. Let's freaking take up that glucose so we can store it where we want to store it, right? The muscle needs a lot of glycogen stores because, you know, being chased by a bear and stuff. How come fat? How come we would want a lot of glucose uptake in fat cells? What's that going to be used for? It's not as obvious. So these are situations where we want to store our energy, right? Because we just ate a big meal. So in the muscle, you can imagine, oh, we'll take up the glucose so we can store it as glycogen. But how about the fat cells? Remember, do we make fatty acids in fat cells? Where do we make fatty acids? What type of tissue, type of organ? Anybody remember? Was it what?
The liver.
Yeah, when in doubt, right? Yeah, it's the liver. So the liver makes the fatty acids, but what happens in the fat cells? Those fatty acids get transported to the fat cells. Do they stay stored as fatty acids? People I was talking about before class, what do they get stored as?
Triglycerides.
So what do those fatty acids have to attach to?
Glycerol.
Yeah, what do we make glycerol from?
Glucose.
Indeed. Yeah. So the reason we take up glucose when we have a lot of it in the fat cells aren't making the fatty acids, but they'll convert the glucose into glycerol so that we can make those triacylglycerides. Okay, so that's what's happening there. Okay, so that is your big full picture of all the things that insulin is going to affect, and we'll come back to this in a little bit and say, man, it must suck to not know insulin is trying to signal. Insulin's knocking on the door and no one's answering. So all those things we mentioned don't happen, even though insulin's trying to tell us to do them. I'm going to try to leave that on the board. So, what I want to do is talk about the cause of insulin resistance, okay? Because right today we're going to put stuff together and start seeing why insulin resistance happens and how it works. And then we'll come back to the consequences of insulin resistance, which has to do with all that. Okay, so in order to talk about the causes of insulin resistance, we need to learn about one more pathway. Remember that table you guys started to make that first day of class, the signal transduction pathways table? Do y'all have it? We're going to finish it.
Yes.
Down on. So we had the CAMP system, and we had the receptor tyrosine kinase system, which is what insulin used. And the one we're going to learn about today is the phosphoinositol system. Okay, so the CAMP signaling cascade, the RTK signaling cascade, again, this was used by glucagon and epinephrine. This was used by insulin, and this is this new one that we're about to learn about that's going to have to do with how insulin resistance occurs. And what do we have on the left side for our table?
Primary messenger.
Okay, and
Signal.
excellent, transducer. What's next?
Primary effector?
Thank you. Secondary messenger and secondary effector. Good. Okay, so with our phosphoinositol system, this is going to be hormones like, let's see, we have GHRH. Anybody know what that one is?
Growth.
My bio majors.
Growth hormone regulating hormone? Releasing hormone?
Growth hormone, releasing hormone, the hormone that releases growth hormone. So that's, pretty important in development. Oxytocin, what's that for?
Love.
We're lacking that right now during this hour and 15 minutes.
That's when my love is strongest, actually.
Social bonding, childbirth, all of those lovely important things. Angiotensin, what's that involved in?
Blood pressure.
Yeah, blood pressure regulation. So, important stuff, et cetera, et cetera. Okay, so that was my first one. Okay, so my transducer. What was it for CAMP? What was my transducer in the CAMP pathway?
GDC.
Yeah, so the G protein coupled receptor. Okay, and this included the stimulatory and the inhibitory alpha subunits, right? Guess what? Phosphoinositol system also works via G protein coupled receptor. Okay. Now, to distinguish it from the CAMP system, instead of the alpha subunit being called GS or GI for stimulatory inhibitory, this one is GQ.
Would that be inhibitory or stimulatory?
It's typically stimulatory. I think that they will let you know if it's inhibitory. Okay. Now, it uses a G protein coupled receptor, and that's pretty much where things end in terms of similarities. What was our primary effector for our CAMP system? What did our G alpha subunit traveled across the membrane and activated who?
Sorry, for which system? Oh, that one.
I'm just comparing it to CAMP.
Oh, adenylate cyclase.
Yeah, adenylate cyclase, the guy who makes CAMP, right?
Yeah.
Yeah, that's the enzyme that makes CAMP. And then I'm just going to finish this off. And then CAMP is going to activate who? Yes.
No.
Yeah. So, in the phosphoinositol system, GQ is going to go travel, and he is going to go activate, instead of adenylate cyclase, he's activating this guy called phospholipase C. Okay, and then we'll look at it on the, whatchamacallit, in just a second. Okay? And instead of, adenylate cyclase created CAMP, the phospholipase C is going to result in the molecules IP3 and DAG. And you'll see what those are in just a second. And then indirectly, that's also going to lead to increasing calcium in the cell. So those are our secondary messengers, IP3, DAG, and then also calcium. Now, the main goal in CAMP was to activate PKA. The main goal in insulin was to activate PKB, otherwise known as AKT. What do you guys think this one is? PKC. Exactly. And he's going to go phosphorylate the world and end up causing all sorts of stuff to him.
Woo!
Calmodulin also gets activated this way. So we learned a little bit about calmodulin last year. Calcium activates calmodulin. But PKC is our main dude. All right, so let's just look at this guy on the slide. You might note that there's something missing from the slide. I have no laser pointer, which sucks. There's something missing from the slide, and that's the receptor. This is like a partial signal cascade diagram. So you might want to draw in a receptor. What do you think the receptor looks like? Think about your table of awesomeness. What do you think that receptor looks like? Would it look like the two guys coming together, like this? Or would it look like the guy going through the membrane 7 times? And why?
Because that's what the G protein coupled receptor.
Yeah, the 7th transmembrane receptor, that was this guy. So that's what these guys look like too, yeah. They also are those ones with all the helices that go through the membrane a bunch of times, and they have the G protein. Okay, so that part's missing from your diagram. You can draw one in if you want, if you're feeling crazy. And it's kind of funny, it doesn't really show you, but then the GQ, that's the alpha subunit of the G protein, will travel across the membrane and it will activate phospholipase C. So phospholipase C is apparently that gray blob, or no, I don't know. They're not even showing you phospholipase C. I don't know what they're doing. Anyway, phospholipase C is like in the membrane and needs activating.
What binds to the decoupled receptor
What do you mean?
to like activate that?
How did you couple proteins work? G protein coupled receptors work. I'm not sure what you're
Oh,
asking.
is it the hormone that binds to the G?
Yeah, and then it's a G. It works the same way in the beginning as our other guy. So the GDP is going to fall out, the GTP is going to bind, G alpha subunit disengages and moves across the membrane. Only now, instead of activating adenylate cyclase, he's going to activate phospholipase C, which is magically not shown in this diagram. Now, what phospholipase C is going to do? There's some PIP2 hanging out in our membrane. Okay, remember PIP2? So PIP2 is just shown right here. Okay. PIP2 looks like that. I have no laser pointer. PIP2 looks like that guy way at top. Okay, no big deal. He's just a phospholipid. So we've got 2 fatty acid chains, and then the third part of the glycerol molecule, instead of a third fatty acid chain, he's got a phosphate group and then an inositol sugar. It's PIP2 because there's 2 phosphate groups on that sugar. Okay. You guys saw him during your insulin pathway. Does anybody remember? He was in your insulin pathway. PIP2 in our insulin pathway. So go to your table. He becomes phosphorylated and becomes what? Yeah, not so here, right? Instead of being phosphorylated and being like, ooh, now I'm PIP3, he's going to get chopped because phospholipase C is what just got activated. So PIP2 is still a precursor in both of these, but it's used very different ways. So in this guy, he's going to get cleaved. That sugar with the phosphate is going to get cut off of the rest of it. So what are we left with? We're left with two molecules. What's one of them? If we cut the sugar off of our PIP2. Right, and IP3, so we cut the sugar off. Inositol was our sugar, and now there's 3 phosphates on it because we cut at the phosphate bridge. So IP3 is just inositol, and then there's 3 phosphates. Okay, it's nothing crazy. And then what's the other thing that we're left with?
Is that the dye?
Yeah, diacylglyceride instead of triacylglyceride, right? Okay, that's going to be important. We haven't learned yet why we care about any of this other than it's a signal cascade, so therefore it's cool. But this is gonna be key as to how insulin resistance occurs. Okay, and then it's just showing you like that the DAG moves across the membrane and the IP3 causes calcium to be released, and the calcium and the DAG then activate protein kinase C, and it goes and phosphorylates a bunch of stuff. That part's not quite as crazy. Now, this is the part where it gets a little bit, it all starts to fit together a bit. One of the targets of PKC, actually somebody remind me, how does the insulin receptor pathway get turned off? So if you go to your PowerPoint 8 from Diabetes 1, is where we talked about that, or you might just remember. The insulin pathway, remember, everything was getting turned on by phosphorylation, right? That was the phosphorylation crazy pathway. How does stuff get turned off? Remember, the pathway, you want to be able to turn it off. You don't want it to be signaling for too long. How do it get turned off?
Is that a self-regulated thing, like self-dephosphorylates or something?
Not quite in an indirect way. So remember, pathway, AKT, right? Here's the membrane. Here's some stuff going on. Eventually, AKT gets activated. And what are some common targets of AKT? Phosphatases, yeah. Remember, if this pathway is getting turned on by stuff being phosphorylated a lot, remember this was negative feedback. So there were some phosphatases that worked to then dephosphorylate a bunch of stuff up here, right? And that was how. So it was like a negative feedback loop. PKC also activates a phosphatase that's going to turn off the insulin pathway. Okay, this is crosstalk between signaling pathways. This is where stuff starts to get like interesting and cool and important. So again, PKC is going to activate a phosphatase. Okay, and this phosphatase is going to then be able to, actually 2 things. There's 2 ways. I messed myself up in my notes. Okay, so first thing is that it's going to activate a phosphatase. It's called a stress-induced phosphatase. And again, that's going to dephosphorylate the insulin pathway. Okay, so that's one way that it can turn off the insulin pathway. Okay, and then the second way is that PKC itself, protein kinase C, remember kinases phosphorylate stuff? PKC can actually phosphorylate IRS itself. So the insulin receptor substrate, if you guys remember that, he's up here. So here's our insulin receptor, here's a little insulin receptor substrate that binds to it. He can phosphorylate the insulin receptor substrate, but at serine and threonine. Remind me which amino acid gets phosphorylated throughout this entire thing? Up here in the insulin pathway? RTK stood for receptor tyrosine kinase. Okay? It's all about the tyrosines being phosphorylated to activate this. PKC phosphorylates IRS at serines and threonines so that it can't be phosphorylated at its tyrosines. Well, think about it. You just stick a bunch of phosphate groups on there that are negatively charged. So probably going to repel more negative charge or probably causes a conformational change, one of those two. Good question. Okay, so here's where everything starts to go bad. So, energy stress, which just means you're eating a lot and not doing anything, okay? This is going to increase your fatty acid supply, okay, which will end up in a lot of your cells, including your liver cells, all right? Your fat cells become full, all right? And so fat starts building up in your liver and your muscles. Anybody had a marbled steak? That lovely bit of fat in the muscle? That's because the fat cells were starting to get like a little bit too full and the fat had to go somewhere else, so it goes to the liver and the muscle. Anybody here fatty liver? Yeah, you don't want fatty liver. There can be non-alcoholic fatty liver disease and alcoholic fatty liver disease, okay? So again, these are situations with like overeating and just the fat starts building up in the liver and muscle. Yeah,
I just had a question. So that is how it's affecting the other pathway, right? That's not how it's like deactivating the pathway itself.
This is how it deactivates the insulin pathway, not its own. I didn't tell you how this gets shut off, and I won't. Yeah.
So I'm assuming its only function isn't to disrupt insulin.
Correct.
So is it growth related?
Oh, it depends on so a lot of different hormones that have very different functions utilize this pathway. Yeah, and in fact, it's hard. It's a good question, Lainey. You're like, how is it that angiotensin and oxytocin, like, why do they have the same response? And it's because their G protein is going to affect phospholipase C in a bit of a different way. It's all a balancing act. Okay, so some are going to activate it more than others. When it's really activated, then it might influence these guys. When it's a little bit activated, it might have this kind of influence. You know, so it's all very fine-tuned. Some GQ proteins again will be inhibitory, and some will be stimulatory.
So insulin resistance is a side effect.
Well, we're going to see. We haven't even talked about how that occurs. We're about to.
Oh, I thought the whole disrupting.
This is not insulin. This is why insulin resistance is going to happen, but it has not happened yet. That's what I was saying. This is all normal and okay up until now. There's no insulin resistance just yet. Okay. This is a normal. Evolution has chosen this crosstalk between these two pathways because it works well in keeping each other in check. So this is okay. What's not okay, as we'll see in a minute, is when fatty acids build up in your liver. So this is a liver cell. Here's the mitochondria. Okay, here's the cytosol. You have fatty acids building up. Typically, when fatty acids enter your liver cell, they go into the mitochondria, right, for beta oxidation. The mitochondria gets overloaded. The fatty acids build up more in the cytosol. They end up turning into triacylglycerides. Well, you cannot have triacylglycerides in your liver cells, so that actually ends up being broken down into diacylglycerides and a molecule called ceramide, which I'll get to in a minute. Tell me what's wrong with all of a sudden diacylglycerides building up in your cell for no reason other than you ate too much. Why would that be a problem? What if we just see diacylglycerides or DAG?
Secondary oxygen.
Yeah. So that pathway we just learned about, DAG was one of the molecules that activates PKC. What happens when we activate PKC? We then turn off the insulin signaling pathway. This is where insulin resistance happens. It happens because when we get too many fatty acids building up in our liver cells, they're going to end up partly as diacylglycerides. So now we have all these diacylglycerides around, not because a hormone told us to make diacylglyceride, but because we ate too much. So we're going to end up activating this guy, not in response to hormones, but in response to overeating. Okay? And so that is going to inhibit our insulin pathway, and that's going to lead to insulin resistance. So now when the insulin binds, fine, it's going to try to do its thing with the receptor, but the signal won't get propagated because PKC has, as soon as stuff gets phosphorylated, PKC is going to end up resulting in it being dephosphorylated, and it's going to phosphorylate that insulin receptor substrate so that it can't, that signal can't go. Okay. So again, normally if this is just a result of hormones, it's fine. But when it's the result of DAG building up in the cell because of this whole mess, that's the problem. That's how insulin sensitivity starts occurring. Okay. Insulin sensitivity is the insulin signal cascade not being able to function. Okay. Now, ceramide is also just a phospholipid. Okay, here, I'll draw you a picture. I like pictures. Okay, so here's my insulin receptor. Okay, here's my PIP3 that gets made, that activates the PDK, that then activates the AKT, blah, blah, blah. Okay. When I have a lot of triacylglycerides build up in the cell, which don't belong in the liver cell, they look like this, right? Here's my triacylglyceride. It's going to get turned into two things. One I told you was diacylglyceride. Okay, according to this right here, the triacylglycerides become diacylglycerides, and they become a molecule called ceramide, or ceramide. I don't really know how to pronounce that. Does anybody remember our phospholipids could have two different backbones? One was glycerol. Anybody remember what the other one was? It was the one that's way more fun to say. It's the one that like are in most nerve cells.
Inositol?
Your phospholipids have a backbone, and oftentimes that is glycerol, but not always. Your phospholipids. Triacylglycerides always have a glycerol backbone. Yeah, spingicine, good. So ceramide, and spingicine was that weird dude where like, it is fun to say. If spingicine was that weird dude where like, he would have his own, he basically has his own fatty acid chain. So he looks like this. He's like, here's my little hydroxyl group, and here's my fatty acid chain, because that's part of the spingicine molecule. And then a fatty acid from somewhere else gets attached to him. And that comes from this, guys. So this is what I'm saying, is that when you break down your triacylglycerides in the liver cells, you get diacylglyceride, so this would just be an OH. But then you also get ceramides, which just look like this. It's a spingicine backbone, which I have in blue, and then a fatty acid that came from these guys. Okay. The reason I went through the trouble of explaining that is that ceramide is going to also be able to inhibit PDK and AKT. Okay. So we already know how DAG can inhibit the insulin signaling pathway. We already talked about that through activating PKC, and we know that PKC has those effects. Ceramide itself has also been shown to inhibit PDK and therefore AKT.
Can you say that one more time?
I sure can. So we already talked about how DAG can affect the insulin signaling pathway because it activates PKC, which then can affect these guys, which by ways we already described. But the ceramide molecule is an inhibitor of PDK. Ceramide is going to end up in the cell membrane, right? Obviously, the fatty acid chain is a phospholipid, okay? But when it runs into PDK, he inhibits it to a degree. So that's going to then inhibit, you know, the activation of AKT to some extent as well.
So that's another way.
That's another way that the insulin pathway is now getting inhibited.
I have a very annoying question.
Please.
Is that different than the rest of your questions, or?
It's a little more annoying, that's why I have to stay. When you're eating too much fat, don't you want to have more triglycerides? But why are you transforming them into DAGs in the first place?
This is in the liver cell. And so in the liver cell, triacylglyceride, for reasons that are not important, when you have fatty acids build up in the cytoplasm of the liver cell because your mitochondria can't oxidize them fast enough, they will eventually form triacylglycerides, but those don't stick around that long. A lot of those will be turned into DAG and ceramide because the liver's function is not to store fat, and so it just doesn't work properly. Yeah. That would never happen. That wouldn't happen in a fat cell. Yeah. Okay. Other stuff that we're not going to get into is the mitochondria gets exhausted and ends up dying, blah, 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 cell death, et cetera, et cetera. Okay. I just liked this part because it's more relevant from what we're learning. Now notice how this is saying like, oh, GLUT4 will then go down. So let's talk about that. Let's circle back to what we started this talk on, which was what things does insulin affect? Because all those things it affects are now going to be SOL because this insulin signaling cascade is not working. So glycogen synthesis and breakdown, no longer working properly because insulin is binding to the receptor, but nothing's happening. I mean, I'm being dramatic because it's still going a little bit, it's just pathetic, you know? It's not, the signal isn't being propagated like it should be, okay? The main problem, the main consequence of this that affects everything else is going to be the fact that GLUT4 will no longer be expressed on the cell membrane because now GLUT4 won't be, or glucose will not be imported into the muscle and fat cells like it normally is. So this is the biggest consequence of insulin resistance, is that GLUT4 isn't expressed anymore. You have all this glucose in the blood waiting to get in, and it can't get in. It's knocking on the door. The door's not there. I guess it can't knock on the door if the door's not there. So this is the problem. So glucose can't get in. Okay? Therefore, how can you make glycogen if you don't have any glucose? I feel like that part on the wall in Pink Floyd. You know which found that now? How can you make glycogen if there is no glucose in the cell? So this is the issue. This is the weird thing about insulin resistance and then, of course, diabetes, is that your body thinks that you're fasting. So you're eating this food, this glucose ends up into your blood, but your cells don't know it because the insulin is telling you to take up glucose, but you're not getting that signal. So you end up with this glucose in your blood, but your cell's thinking that you're starving, that you're not eating anything. So what's going to happen in that case? Autophagy will occur eventually, but what do you normally do? So if you guys fast, what happens?
Pass out.
I mean,
Hungry?
geez, that was extreme.
Okay.
Biochemically, let's go back to that. So according to this slide even, and your fat cells will do what? If it thinks like, oh, I haven't eaten in a while. They'll break down fats, right? So we have lipolysis occurring. Remember, your body thinks that you haven't eaten in a while. So the triacylglycerides will get broken down into glycerol and fatty acids. Fatty acids will be like, here we come to save the day. And like,
It's my nails.
They get to the cell, and into the cell they go, and they're ready to they become acetyl-CoA, and they're ready to enter the citric acid cycle. And oh, no glucose can get in the cell. Do you have any citric acid cycle intermediates? So what are you going to do with that fatty?
I thought it would be the other way around.
That's a complicated question that we'll get into. Yeah, that we'll get into more on Wednesday. So you have ketone bodies being sent out. So what are some markers of insulin resistance? Some markers are that you have a lot of fatty acids in your blood. Some markers are hyperglycemia. So hyperglycemia just meaning that you have a lot of glucose in your blood. Think about the reasons you have a lot of glucose in your blood, guys. There's a number of them. One is that GLUT4 is not being upregulated on your cell membrane. So the glucose can't get in as well. It can still get in through those other ones, but the other reasons you have a lot of glucose in your blood are what? What's your liver going to do if it thinks, oh my God, my other cells don't have any glucose. I need to save the day. I'm going to do what? Yeah.
Be unnecessary.
Yeah, your liver cell is going to start breaking down glycogen and doing gluconeogenesis and sending out more glucose to your cells because it thinks that, nobody's getting glucose. Okay, so you end up with a lot of glucose in your blood. You end up with fatty acids in your blood. You end up with a lot of ketone bodies in your blood and your urine. And you end up, if things go really bad, with acidic blood pH. Life sucks. Don't overeat. Like, a lot.
Here for a good time, not a long time.
Make sense? Questions?
What was the last thing you said? The fatty acid, glucose, and something else.
Fatty acids are in your blood. So you end up, when you get blood work done and your doctor's like, oh, damn, you are insulin resistant. It's because they found high glucose levels in your blood, they found high fatty acid levels, they found high ketone levels. And again, if things are really bad, you might have had acidic blood pH from the ketones. Yeah.
Thank you.
I'll ask you a question. So is that what DKA is?
Is that what is?
DKA?
Yes.
Okay.
Boom. Taking care of business.
Thank you. Diabetic
Ketoacidosis.
Ketoacidosis. All right, that's pretty much my spiel. This last slide I'm going to save for Wednesday. Otherwise, mountain. So we'll talk briefly about these ketogenic diets and
Wait, there's no way that class is done right now.
class is done. This is always my shortest lecture of the year. This is
We
the only
never
short
got out.
because last year you asked so many damn questions that we had to finish the.
All right, I'm gonna
wicked
stop the
one.
video before you just